Okay, so this one I have shared. So if you wish to have like prior knowledge for this topic, okay, it's good to look at this list of YouTube videos because it has animation, right? Since if it is animation, it's easier for you to understand, especially when we talk about history of atomic model, electromagnetic productions, electromagnetic EM, what we call as EM just now, electromagnetic radiation, because this is the first that you need to understand what is electromagnetic radiation. Okay. So before I proceed, I would like to ask anybody to volunteer on what is your prior knowledge? What have you gone through if we talk about quantum chemistry? Anyone? Or what do you understand when we talk about quantum chemistry? Anyone who has mic or anyone who can willing to share what do you know or what have you come across when we talk about quantum chemistry? Anyone?
We see something at atomic level.
Schrodinger, atomic level. So have you discussed Schrodinger before? Yeah, atomic level is correct. Have you discussed Schrodinger equation before?
Yeah, last semester.
Last semester, in which topic? In which subject?
Basic physical chemistry.
Basic CHM3000.
Yeah.
I
I think so.
see. Okay. So what about atomic model? Have you discussed the history of atomic model, for example, Rutherford, J.J. Thomson?
Yeah.
Okay. So I'm quite confused which one has not been covered. So if anyone can tell me if you remember what is J.J. Thomson all about? just a brief one. So do you remember the plum and pudding model? This is Dalton, so I'm not going to discuss Dalton. Anyone remember the plum and pudding model? But it's okay. If you don't remember, just say that you don't remember, okay? So you have come across this, right?
Yes, Prof.
Yes.
All right. So you have gone through this. So by right, you also have discussed cathode rays, right?
Yeah.
Yes.
Okay. CHM3000 lah. So I don't know why that you have to take that and then you have to take this one as well. So it's okay. Then we can move on. So I just want to recap back what you have gone through before, just to review back before we proceed to the more on the electromagnetic radiation. So these are the key of history of atomic model. So before you understand the structure of atom, we need to know the history first, because if you don't understand the evolution, not to say it is evolving, but the first scientists, like they say A, B, C, and the second scientists do another experiment. They've observed a different and then observation, and then they have different conclusion. Okay, so whenever that we talk about science, finding of science, is good, of course, to know the name of the scientist. Okay, right here, you know, there's J.J. Thomson. And we should also know about the experiment. What is the experiment that he has done? And the third one is what is the conclusion, the theory, or the model that the scientist is proposing. Yeah. And then comes the next one comes Rutherford. So have you discussed Rutherford before?
Yes, Prof.
Ah, right. Thank you. So what do you remember about Rutherford experiment?
The deflection of alpha particle.
Yeah, very good. Okay, so I don't have to do that again. So how does Rutherford like prove the J.J. Thomson model is wrong? Okay, this is by J.J. Thomson, yeah. But Rutherford has different view. So how does J.J. Thomson, sorry, how does Rutherford prove that J.J. Thomson model is wrong? Based on his gold foil experiment, deflection of the alpha particles, okay, right? He managed to like, not to say manage, he actually corrected the plum and pudding model. So which part of this that you think, if it is plum and pudding model, what are the observation? Yeah, any ideas? Okay, if I draw here, this is, let's say, plum and pudding model by J.J. Thomson. Okay, what do you think will happen to the alpha particles? Anyone has idea what happened to the alpha particles if the J.J. Thomson model is correct? Okay, so you see that this is by Rutherford, and the most important observation is most particles pass through, right? That's the most important observation. Only certain alpha particles is deflected back. Only some small amount of alpha particles deflected back, but most, yeah. So this is the key word, the key point, most pass through. So what is the conclusion from that is, if the J.J. Thomson model is correct, then we should see a lot of alpha particles being deflected back, okay, by right. So this proves that there's something wrong with the J.J. Thomson model. So this lead to new structure of atom, which is we have that atom contain a lot of empty space. Yeah. So it's not really okay. So moving. Atom has empty space, a lot of empty space. Yeah. Let me erase that. A lot of empty space, and in the middle, okay, there is a densely positive charge, which is here. So that is the implication from Rutherford experiments. Okay, so this is a process starting from the first scientist and moving on to the second scientist. So this is again the conclusion from Rutherford Goldfall experiment. Okay, let's move on. Since you have done all this. So this is also the structure of atoms. So I'm not going to do this. And you understand the isotope already from CHM3101. Okay. So I hope this is not something new for you. Okay. And so this is where you start to learn about the quantum mechanics. Okay. So since you have come across Schrodinger equation, okay, being introduced to you Schrodinger equation, can someone just tell me what you remember, what is actually Schrodinger equation for? It's okay.
Shape
Anyone?
of orbital.
Is about?
Shape of orbital.
So you relate a Schrodinger equation with shape of orbital. Is that so?
Yeah.
Yeah, okay. All right, it's okay. It is related. Okay, anyone else has ideas on what Schrodinger equation is?
The behavior of the quantum system.
Quantum system. What do you mean? What do you understand? What when you say quantum system?
The behavior.
Behavior of electron or what?
Um,
It's okay.
Atom, molecule, particles, all.
Okay, it's okay. All right. So we talk about quantum mechanics or quantum chemistry. We are talking about the characteristic of especially electrons. Okay, which is small particles. Okay, they don't behave like big particles. Okay, like for example, if you see a ball in front of you, if you see a ball is considered a big particle. Okay, so you can see actually it move around you. Okay, you also can pinpoint or talk about the location of the ball, because you can see, okay, someone is playing football in front of you. You can see the ball moving here and there, so you know the ball is moving to the right, to the left, or whatsoever. Okay, so that is big particle. But when we talk about a small particle like electrons, electrons is very, very small. So now the characteristic is different. So this is what we call as quantum. The movement of electron and the whereabout of the electron is actually impossible to be determined uh, at the same time. Okay, so that's why we are talking about quantum theory, because we are trying to talk about the characteristic of small particle. Okay, because it is a totally different characteristic compared to big particles or big object like us. Okay, so one thing, Schrodinger equation is about function, right? If you look at the equation, we are talking about the function of electron. Okay, so I don't have in my slides the Schrodinger equation, but we will discuss that in class. Okay, you can see that it relates in terms of momentum, right? And the location of the electron. So it is true that from the Schrodinger equation, we can have the probability of finding electron, and it is related to orbital. Orbital is where a place you can find the probability, a high probability of finding electrons. So that is what orbital is. Yeah. So if you wish to know more about quantum, okay, this is a very good documentary in YouTube. Okay, so they share how the previous scientists comes to discussion, their views on. This is very interesting, especially this was the first one talking about the quantum world. Okay, so I hope that if you have time, please do watch this documentary. Okay, so when we talk about quantum mechanics, okay, I prefer to say quantum chemistry. We are referring to more on electrons. Okay, and before this, they treat electron, means that the understanding of scientists, they understand that electron behave like particles. Okay, they behave like particles. So when we talk about particles, means that electron has mass. Okay, you can see their movements. Okay, so just like big particles like like we human, like the balls just now. Okay, you can weigh the mass, you can see the movement. Okay, so that is particle all about. So in understanding before the quantum mechanics, quantum theory comes about, is they understand that electron behave like particles. Okay, so it's quite easy to understand when we talk about particles. Okay, so have you discussed about quantization of energy before? It's okay, because today I would like to know what your previous knowledge on. Just tell me, what do you understand about quantization of energy? Photon? Have you heard about photon?
Yes.
What do you understand about photon? Can we have someone else talk about photon? Idina, are you there? Idina, what do you understand about photon?
They
Azam?
have
Sorry,
mass.
Idina. Okay, photon.
They have
Okay.
mass.
It has mass.
Mm.
And then
Electron.
energy. Yeah?
Yes,
All right.
energy.
Okay. So, all right. Thank you, Idina. Azam, what do you understand? I see Azam here. Azam, can you tell us what do you understand about photon or quantization of energy? Okay, yeah, Azam, yes, please.
Dia photon emit,
Uh-huh.
dia menurun dan dia naik.
Menurun dan menaik.
Dia emit dengan apa? Tak ingat lah.
Tak apa, it's okay. Whatever that you can remember. Okay. Let me move to the. You're talking about this one, right? Ni, this one kan, Azam?
Ya, Prof.
Yeah, right. So this is photon emitter. Okay, so okay. So I hope by now, since we have discussed, okay, this is how electromagnetic, okay, right? This is just a moment. It's taking some time to move back. This is, I hope by now you know what is electromagnetic radiation. Consists of different energy level and different frequency of a series of radiation. Okay, so all this radiation has its own energy level, its own wavelength, as well as its own frequency. Okay, so how does electromagnetic radiation is mentioned just now by Azam. Okay, but I just want to test you if it is higher in lambda, the energy is lower or greater. It should be lower. You can see that the lambda here, lambda wavelength, right? The wavelength of the radiation is bigger. Okay, the energy is lower. Especially if you look at here, you don't expose yourself to X-ray or UV. I mean, but you always play around with radio wave. So it's fine to expose yourself to radio wave, but we don't expose ourselves to gamma rays. Yeah, purposely exposing yourself, because we know these are all high in energy. So you can see that the wavelength is low. Okay, So this I think you should be familiar with. So, and but then how it is produced, how it is produced is very important. So this is what Azza mentioned about the photon. Okay. So we know electron, okay, and then we know orbital. All right. And we know the process of if there is energy provided, okay, or bombarded to the atom, okay. So this is energy, and the electron will be excited. The word excited here. The electron will be excited and to a higher energy level or a higher energy orbital. Okay. And then what happened after that is the electron cannot stay there. It has to go down, okay, what we call as relaxation process. Okay, so because of the higher energy, okay, it is not stable, so it has to undergo relaxation process. And of course, this is the word Azza mentioned just now, photon emission. Okay, so photon is energy. Yes, it's true, it has mass because it consists of electrons, energy. Okay, so the issue here, what does quantization of energy related to this process? Anyone can say something on that? Because the issue that we want to know is quantization of energy. So how does quantization energy relate to this? Sheila, are you there?
Yes.
So what does quantization of energy related to this process? I cannot find my eraser. Oh no. Sorry. No, I have, all right. Move everything. Okay. So how does quantization energy relate to this process? Okay, anyone else? It's okay, don't worry if you cannot answer. We have Muhammad Afiq. Muhammad Afiq, can you share with us anything that you understand?
When
Hmm?
yang saya faham,
Hmm.
dia apa, kalau photon tu keluar,
Hmm. Dia.
nanti energi berkurang.
Okay, tak apa, it's okay. All right. Okay, we have Haris. It's okay. Haris, can you also share with us what you understand? Yes, Haris, can you speak up?
Sekejap.
Tak apa, take your time.
Mana actually?
Tak apa, it's okay. If you don't remember, it's fine. Okay. So I think you have understood this well. Okay, some of you might be. Okay. Why is it moving? Okay, just a moment. All right. Okay. You understand the process. Electron receive energy. Okay, if you bombard certain energy to the atom, okay, like you heat it up, you microwave, you whatever you do towards the atom, so the electron inside the atom will be excited. So of course, when you provide energy, you know the level of energy that you provide, and the electron will absorb. Yeah? The electron will absorb the energy. So consider if the energy absorbed is E1, the value is E1, and it only jumps, okay, it only jumps to the orbital with the level of E1 energy only. Okay, means that the value here, the difference of value of between the orbital must be E1. Okay, I hope you understand that. And then if it requires to like relax to the ground level, let's say it goes to the ground level orbital, it will also emit, okay, the same value of energy, okay, called photon. Photon is actually a bucket of energy, a bucket, yeah, called photon with the same value. So that is quantized, okay, quantization of energy. You cannot like force, okay, the electron. Let's say we have n equal to 2. This is n equal to 1. So you want the electron to go to n equal to 2, but you provide only this amount of E1. Okay, let's say you provide only 20 kilojoule of energy. So this 20 kilojoule only can survive or only can be excited to n equal to 1. But you think that by providing the energy for 2 hours, 3 hours, 4 hours, or 24 hours, you think that the energy will be concentrated, the energy will be, you know, stored, and then it goes to n equal to 2. No, no. And the concept of quantization of energy, if you provide 20 kilojoule, it only goes to orbital that have the same energy. It cannot go beyond n equal to 1, for example. Okay, and same goes when it goes down, it will release the same amount of energy. So that is quantization of energy. Okay, it is fixed. The photon being reduced, the photon being released is with specific amount of energy. Okay, so this is how you get this. So anyone, have you discussed atomic spectrum before in CHM3000?
Yes.
Yes. So what do you understand about the production of atomic spectrum or emission spectrum? It's either one. How do they get these lines?
Based on the lambda.
Okay. So the process just now, okay, n equal to 1, let's say n equal to 0, n equal to 1. Yeah. Right. And then we talk about the electron, right? And then the electron excited with certain energy. Okay, once the electron goes down, okay, you will have a photon, okay, photon with certain energy, which is supposed to be equivalent to the energy that you have given. Okay, so this is how you get the lines. Okay, so the lines here represent the energy absorbed. Okay, if it is absorption spectrum. Okay, and it also can represent energy emitted during this process. Okay, then you have emission spectrum. So you can have absorption spectrum, atomic absorption spectrum, or you can have emission spectrum. Okay, you can have both, depends on what you want to measure. Okay, so this line is representing the energy absorbed or emitted by the electron during the process of excitation, and or you want to measure the process during emission, or when the electron goes back to the lower orbital level. So this is what you get called emission spectrum or atomic absorption spectrum. Okay, right. So why this is important? Because these lines is unique to each element. For example, if you have like sodium, okay, sorry, I put plus, doesn't have to be plus. Potassium, calcium. So each of these will have different or will have unique absorption or emission spectrum of its own. So this is like a fingerprint. Like human, we have DNA, right? For element in periodic table, they have this atomic absorption as well as emission spectrum unique to them. Okay, so why does we have all this unique to the element? Anyone? Aina dan Sarah? Why do you have two names? Aina and Sarah? Why is the emission spectrum or the absorption spectrum unique to the element in periodic table?
What is the
Huh?
hydrogen?
No. My question is why? Yeah.
Oh, why?
Because why
Yeah.
is the emission spectrum or absorption spectrum unique to each element?
Why? Kenapa you
Kenapa dia unik? Why?
different atom?
Like us, we have DNA unique to us, right?
Proton ke berbeza?
Electron. We're talking about electron.
Electron. Sorry, doctor.
Proton is inside the nucleus. Okay, we don't discuss the characteristic of proton, yeah, unless we are talking about nucleus, nuclear energy or nuclear chemical reaction. Okay, so we know that each element has different number of electron, yeah, and they also have different electron configuration. So this is translated into different emission spectrum or different absorption spectrum. Okay, because we understand the electron will be moving up, going down, so it will be a unique pattern for each element. Okay, so that's how emission spectrum is being used. Yeah. Okay, so this relates back to quantization of energy. Okay, this is the most important. Sorry. So this is the most important that I want you to understand. I don't know, I mean, you have gone through in CHM3000. Quantization energy means that the energy is fixed, okay? If the electron receive 20 kilojoule, it can only go to the orbital that suits 20 kilojoule. It cannot go beyond. And then if the electron goes down, with the same different gap between the orbital, it should release the same energy amount of 20 kilojoule as well. Okay, so the energy emitted or the energy absorbed, it is called photon. Okay, so you have to like imagine that the energy comes in a bucket dalam baldi. Okay, the electron receive energy in a specific amount. It is not like increasing from 20 and increase to 21, 23, no. Yeah? If it is 20 kilojoule, it will receive the electron, the energy in 20 kilojoule at one time. Okay, so that is quantization of energy. Please do understand that, okay? And these are the things that we need to discuss before we understand about photoelectric effect. Okay. So the last part for today is photoelectric effect, but we will discuss in more during the class. So this is a setup of photoelectric effect. I think I have it. No. Okay, I will share with you. the photoelectric effect, or someone, or have you come across about the photoelectric effect experiment before?
Yes.
Okay, good. So this is more or less, you have a metal plates, right? Okay, and then bombarded by certain amount of energy, and then you have electron. What happened to the electron? I think I can play the YouTube.
Explore low-price flight maps on the Trip.com app. Book low-cost flights now.
Lain pula keluar.
Hey, Barb.
Hey, it's Professor Dave. I want to tell you about wave-particle duality.
He knows a lot about the science stuff. Professor Dave explains.
So let's take a break from atoms and look at something else, light. For some time, we had known light to behave as an electromagnetic wave. For this reason, light is also called electromagnetic radiation. Light waves have both a wavelength, the distance from tip to tip, and a frequency, the number of waves that pass by a point per unit time. They are inversely proportional, since the shorter the wave, the more of them that can go by per second, resulting in a higher frequency. These variables are related by the following equation, in which c is the speed of light.
Skip.
This was the observation that if a certain metal plate is irradiated, the light we can detect with our eyeballs. The wave theory of light was very useful for a time, but it could not explain the photoelectric effect. This was the observation that if a certain metal plate is irradiated with light, an electron is ejected, which can be detected when it interacts with a positively charged wire or plate sensor. The incongruity was that the ability of the light to eject an electron depends only on its frequency and not its intensity. So if the beam was below a certain frequency, even a very intense beam with a lot of light could not eject an electron, whereas above a certain frequency, the faintest beam possible could do it. This seemed strange, and a famous fellow named Albert Einstein solved the problem by extending a concept developed by Max Planck just 5 years prior. Planck proposed that energy is not continuous, but rather is quantized. That is, all energies are multiples of the smallest fundamental unit of energy, the Planck energy. In fact, quantum theory went on to show that everything is quantized, space and time too. So you can't infinitely subdivide them, you'll eventually get to a smallest thing that can't be divided further. But more on that in the physics course. Einstein extended what Planck said about energy and rationalized that light must also be made of quanta, which he called photons. These are particles of light. This explained the photoelectric effect because an electron is ejected when struck by a singular photon with sufficient energy. It only takes one photon, so even the faintest beam above a certain frequency will be able to do it. But if none of them are of that minimum energy, no matter how many photons strike the sample, an electron will not be ejected.
Okay, so I hope that you hear that. I don't know whether you can hear or not. Okay, if the energy amount is enough, okay, specific, let's say if it is required for that metal to have 30 kilojoule of energy in order to eject electron, okay, so only 30 kilojoule is enough. If you have below than that, even though you shine the lights 24 hours, it will not be ejecting any electron. Okay, so if you have like 30 kilojoule, then even a single photon can eject electron. So let's say if you have higher than 30 kilojoule as well, you can only you can of course eject the electron, but that is not important, because the most important is the minimum energy. And the minimum energy required depends on the types of metal. Okay, for example, if you are using copper, it requires different energy. If you're using magnesium, if you're using gold, it requires different energy. So this is photoelectric effect. Okay. Okay. So because this is important, there are calculations for photoelectric effect, and I will discuss the calculation in class. Okay, but the most important one, I would like you to review back the observation and the conclusion, not conclusion, is conclusion from the photoelectric effect. So I hope by next class, we can discuss the photoelectric effect to focus on observation, conclusion, and we will discuss also calculation. Okay. So I think that's it for today. I just want to ask about the groups for SCL. Sorry, let's stop the recording first.